So you see, everything we did in this video was in service of answering this very common interview question. Hello, welcome to the final lesson in our free module from the Networking Fundamentals course. This lesson is the summary lesson to everything we have learned so far. The purpose of this series was to teach you the very core of networking, how data flows through a network. In this series, we talked through the OSI model and the different functions each layer is responsible for. We talked through how hosts on the same network communicate with each other, regardless of how they are connected. We talked through switches and how they facilitate communication within a network. We also talked through how hosts on foreign networks speak with each other, whether they are connected behind one router, or multiple routers, or on opposite sides of the internet. We discussed what routers do, and how they learn routes and hand data off to one another. We covered each of these things in detail in prior videos in this module. And in this lesson, we're going to tie elements from each of those videos together into a comprehensive summary lesson. At its core, understanding how data flows through a network comes down to understanding three specific tables: a MAC address table, an ARP table, also referred to as an ARP cache, and a routing table. Each of these tables is a mapping of something to something else. A MAC address table is a mapping of a switch port to a MAC address, and an ARP table is a mapping of an IP address to a MAC address, and a routing table is a mapping of an IP network to an interface, or an IP network to an IP address of the next router in the path, also known as the next hop IP address. These three tables are crucial to moving data through a network, and we're going to show you everything that happens with these three tables as data is flowing through this network topology. This topology has three routers, routers 1, 2, and 3, and three hosts, hosts A, B, and C. Each host exists within a network, and all the devices have IP addresses in their respective network. And finally, each of these wires are connected to NICs, and each of those NICs have unique MAC addresses. And again, I'm only showing you the first 4 digits of MAC addresses to keep things simple. Now, in the case of the switch, since we are only sending traffic through the switch and not to or from the switch's MAC address and or IP addresses are irrelevant. We elaborated on this point back in lesson 4. So for our switch, we only need a label for the two switch ports that these wires are connected to. In this case, they're going to be port 4 and port 5. Each of the devices in this topology are going to use one or more of these tables to process data, and we're going to show them to you in these gray boxes. Our switch is only going to have a MAC address table, and you're going to see the entries of the MAC address table right there. Our routers have both an ARP table and a routing table. And our hosts, being very similar to routers as we discussed back in lesson 5, also have both an ARP table and a routing table. Now both the MAC address table and the ARP tables are going to be populated dynamically as traffic is flowing through this network. The routing table, however, must be populated ahead of time. Recall that back in lesson 5, we said that if a router receives a packet with a destination IP address not in the routing table, that packet would be dropped. So at this point, if our host started sending packets, since our routers have empty routing tables, everything would just be dropped. Therefore, the routing tables must be populated before any data can be sent through this topology. So let's fill in all the entries for all the routing tables in this topology, starting with host A's routing table. Host A only needs a default gateway, also known as a default route. The default route will be represented as a route for the 0.0.0.0/0 network, which includes all IPv4 addresses. This route is pointing to the IP address of this interface of router 1, 11.8.8.1. This will tell host A to use router 1 anytime it's trying to speak to anything on a foreign network. Host B will also have a default gateway pointing to this interface IP address on R2, 22.7.7.1, and host C will also have a default gateway pointing to this interface IP address on router 3, the IP address 33.6.6.1. Each of our routers will have two routes. First, they will have a directly connected route for the networks that they are attached to. Notice R1 has a directly connected route for the 11.8.8.0/24 network. Then, each of the routers are going to have a default route pointing to the internet. Now normally, that default route would point to a specific router IP address somewhere on the internet. But to keep things simple, we'll simply abstract that away and say that this route is pointing simply to the internet. And now we are ready for host A to send some data. I want to show you the details of this data, but there isn't enough room here to show you the source and destination information. Instead, I'll show you this data in more detail in this box right here. Inside this data payload is just a bunch of ones and zeros. The network doesn't know or doesn't care what specifically those ones and zeros are doing. It's just arbitrary computer code that needs to be sent to another host. Host A will start by adding a layer 3 header to this data. This will facilitate the end-to-end delivery of this data. To begin, host A will be sending this packet to host B. So the source IP address of this packet is going to be the IP address of host A, 11.8.8.11. And the destination IP address of this packet is going to be the IP address of host B, 22.7.7.22. And now we are at the starting point of our illustration, and we are ready to follow this packet as it travels through this topology. The first thing that happens when host A is trying to send this data is host A will compare the destination IP address of the packet with its own IP address and subnet mask to determine that the destination IP address is on a foreign network. Therefore, this packet must be sent to host A's default gateway, which is router 1. But at this point, host A's ARP table is empty, which means host A doesn't know router 1's MAC address, and therefore is unable to put together the necessary layer 2 header, which will take this packet across this hop. So host A will hang on to this packet and first go through the ARP process to resolve router 1's MAC address. The ARP request is also going to have a layer 2 header. That layer 2 header is going to have a source MAC address of host A and a destination MAC address of all Fs. That's the broadcast MAC address. This will tell the network that this ARP request should be sent to everybody in this network. When host A puts that on the wire, it'll arrive on our switch. Anytime something's received on a switch, it's going to try and learn the mapping between the receiving switch port and the source MAC address. In this case, the source MAC address of this frame is A1A1, and the receiving switch port is port 4. Therefore, our switch is going to learn that something out port 4 owns the MAC address A1A1. Then, the switch is going to look at the destination MAC address. In this case, the destination MAC address is all Fs, which tells the switch that no matter what, it's going to do the flooding action to send this frame out all ports. Now in our topology, there's only 2 devices in this network. But if there were other devices plugged to this switch, they would also receive a copy of this frame. But for us, that frame would only be sent out port 5, where it'll arrive on router 1. Upon arriving to router 1 will get to learn the ARP mapping of the sender. Recall that when we discussed ARP, we told you that inside the ARP request is the ARP mapping of the sender. So by simply receiving the ARP request, router 1 is able to learn that a device with the IP address 11.8.8.11 maps to the MAC address A1A1. Then router 1 will generate an ARP response. This ARP response is going to look like this. It's going to have a source MAC address of router 1's NIC and a destination MAC address of host A. This is a unicast ARP response meant to be delivered directly back to host A. Router 1 will put that on the wire, where it'll arrive on our switch. And again, just like before, since the switch received something on port 5, it's able to learn that a device out port 5 owns the MAC address EEE1. Then the switch will again take a look at the destination MAC address. In this case, the destination MAC address is A1A1, and our switch already knows that that MAC address exists out port 4, and will therefore forward this frame out port 4, where it'll finally arrive back to host A. Once host A receives it, host A will learn the MAC address that it was trying to resolve. In this case, that the IP address 11.8.8.1 maps to the MAC address EEE1. And now, host A has the necessary information to complete this layer 2 header, which will take our data packet to the router. That layer 2 header will have a source MAC address of host A and a destination MAC address of the router, now that host A knows the router's MAC address. This layer 2 header will handle delivering this packet across its first hop, which in fact is the goal of layer 2, hop-to-hop delivery. Now if that idea isn't familiar to you, we unpacked it when we discussed the OSI model back in lesson 2. Either way, host A will put all of this onto the wire, where it'll arrive onto the switch. Once it gets to the switch will again try and learn what it can from this incoming frame, this frame arrived on port 4 and had a source MAC address of A1A1, and our switch already has that entry in its MAC address table. So there's nothing new for the switch to learn, but this particular entry will be refreshed in the switch's MAC address table. Then again, the switch is going to look at the destination MAC address to determine that this frame should be forwarded out port 5, where it'll put it on the wire and send it out towards router 1. Once that arrives to router 1 will strip the layer 2 header. The purpose of that header was again to take the packet from host A to router 1. It did that successfully and we no longer need it. Then router 1 will take a look at its routing table to determine where it's going to send this packet next. The destination IP address of this packet is the IP address 22.7.7.22, which matches this route for router 1, which means router 1 knows that this packet is going to be sent across the internet. As we discussed earlier in this module, the internet is really just a bunch of other routers that'll hand data off to one another. And normally, this route would point specifically to one of these routers. But we unpacked the details of how routers hand data to other routers back in lesson 5. So rather than repeat myself, I'll simply direct you to that video if you want more information on this process. I'll also mention that there are actually many more ways that this packet can get through the internet to router 2. All of those ways are contained in what's known as WAN technologies, and the details of each of them are outside the scope of this module. One way or another, this packet will be passed from router to router across the internet until it finally gets to router 2. And when it gets to router 2 is going to take a look at its routing table to try and figure out how to deliver this packet. The destination IP address of this packet hasn't changed, which means this packet matches this route, and router 2 knows it's going to be delivering this packet to its final hop within the directly connected network that router 2 is attached to. However, at this point, router 2's ARP table is empty, which means router 2 is unable to put together the layer 2 header necessary to take this packet to host B. So just like before, router 2 is going to have to put that packet on hold and send out an ARP request. The ARP request will be sent to the broadcast MAC address, but this time the source MAC address is going to be router 2's MAC address. This packet will be put onto the wire where it will arrive on host B. Upon receiving the ARP request, host B gets to learn the ARP mapping of the sender of that ARP request. In this case, the IP address 22.7.7.1 maps to the MAC address EEE2. Then host B will generate a response. That ARP response will look like this. It's going to be a unicast frame sent with a source MAC address of B2B2 and a destination MAC address of EEE2. That ARP response will be put onto the wire where it will arrive on router 2, and router 2 will learn the ARP mapping that it was trying to learn, that the IP address 22.7.7.22 maps to the MAC address B2B2. And now router 2 has all the information necessary to put together the layer 2 header that'll take this packet to host B. That layer 2 header is going to have a source MAC address of router 2 and a destination MAC address of host B. Router 2 can now put the packet on the wire where it'll finally arrive on host B. Now, normally you wouldn't see a host plugged directly into a router. Normally, this host would be connected to a switch, which would then possibly be connected to other switches, which would then finally connect to the router. But we've already illustrated a switch's operation back here, and we discussed how frames travel through multiple switches back in lesson 4. So to keep things simple, this network does not have any switches. But if you want to understand how data flows through multiple switches, check out lesson 4. Either way, once this packet arrives on host B, the first thing host B does is strip the layer 2 header. Again, that header only existed to take this packet from router 2 to host B. The next thing host B does is strip the layer 3 header. Again, the purpose of that header was to handle the end-to-end delivery of this data, which it did so successfully. And now host B can finally process all those ones and zeros contained within that data payload. Once it's processed that data, it can now generate a response. And that response, just like before, is simply a data payload which includes a bunch of ones and zeros. And now we'll step through all the steps required to get this data payload back through the network to host A. Now, what you'll see is that this is going to go much quicker than before, because most of our tables have already been populated. host B will start by throwing a layer 3 header onto that data. That layer 3 header is going to have a source IP address of host B and a destination IP address of host A. In this case, since this packet is going to something on a foreign network, we know that it must be sent to router 2's IP address. And at this point, host B already has the ARP mapping for router 2's IP address and can therefore already put together the layer 2 header necessary to get this packet across its first hop. This is what will allow this packet to make it across this hop. Upon arriving on router 2 will strip the layer 2 header, and then router 2 will take a look at its routing table to figure out where this packet should go next. In this case, the destination IP address 11.8.8.11 only matches the default route, so router 2 knows that this is going to be sent out towards the internet. And again, we've abstracted that process out, so it'll be handed from router to router across the internet, where it'll finally arrive on router 1. Upon arriving on router 1 will take a look at its routing table and determine that the destination IP address matches the directly connected route, so router 1 knows that this destination IP address is the final hop for this particular packet. And router 1 also happens to already know the MAC address for that particular IP address. So router 1 has all the necessary information to put together a layer 2 header that'll take this packet across its final hop. That layer 2 header is going to have a source MAC address of router 1 and a destination MAC address of host A. Router 1 can then put that packet onto the wire. It'll arrive on our switch, and just like before, our switch is going to try to learn. It'll try and map the receiving switch port, which is 5, to the source MAC address of the incoming frame, EEE1, and it'll notice that it already has that entry in its MAC address table. So there's nothing new to learn, so this entry will simply be refreshed in the switch's MAC address table. Then the switch will look at the destination MAC address A1A1, and the switch knows how to deliver a frame to the destination MAC address A1A1. This frame will be sent out port 4. It'll then finally arrive back on host A. Host A will strip the layer 2 header. Again, that header took the packet from this NIC to this NIC. Host A will then strip the layer 3 header, which took the data from this end to this end. And finally, host A will process that response data. So we just showed you everything that happens to get data from host A all the way to host B and back again. And we showed you how each of the devices involved in this process used a MAC address table, an ARP table, and a routing table to make that happen. Next, host A is going to send some data to host C. Now, if you feel that this is beginning to get repetitive, awesome. That's great. That's exactly right, and it means you're learning how it all works. Remember, all these devices, hosts, switches, routers, all follow simple, consistent packet processing rules. And if you understand those rules, you can scale this topology to hundreds of devices and still walk your way through each step necessary. For this last packet, going from host A to host C, I want you to test yourself. Try to guess what happens next at each step just before I explain it. With that in mind, the first thing that host A does to send this data to host C is throw a layer 3 header onto that data. That layer 3 header is going to have a source IP address of host A and a destination IP address of host C. Then, since host A knows this packet is going to a foreign network, host A is going to look at its default route to determine the default gateway's IP address, which is router 1. And since host A already has the ARP mapping for its default gateway's IP address, it can already put together the layer 2 header, which will take this packet to router 1. That layer 2 header is going to have a source MAC address of host A and a destination MAC address of router 1. Host A will put this onto the wire, where it'll arrive on the switch. The switch will try and update its MAC address table with an entry for port 4, mapping to the source MAC address A1A1. Since that entry already exists, that entry is simply going to be refreshed in the MAC address table. Then the switch is going to look at the destination MAC address to determine where to send this packet next. That MAC address exists out port 5, which will have this switch send this frame out port 5. It'll then arrive on the router, and the router is going to strip the layer 2 header. And now router 1 is going to look at its routing table to determine where to send this packet next. The destination IP address on this packet matches the default route, which means router 1 is going to send this packet across the internet, where it'll finally arrive on router 3. When router 3 gets it, router 3 is going to again look at the destination IP address and determine that it matches the directly connected route in router 3's routing table. This tells router 3 that it's going to have to put a layer 2 header onto this packet that matches the MAC address associated with this IP address right here. But at this point, router 3 does not have anything in its ARP table, so it cannot put together the appropriate layer 2 header. Therefore, just like before, router 3 is going to put that packet on hold, and then router 3 is going to send out an ARP request. That ARP request will be sent to the broadcast MAC address, which will ensure that this ARP request gets delivered to everybody on this particular network, which means host C will definitely receive that ARP request. Upon receiving the ARP request, host C will learn the ARP mapping of the sender of that ARP request, which in this case is the IP address 33.6.6.1 and the MAC address EEE3. Then host C will put together the ARP response. That ARP response will look like this. The ARP response is sent as a unicast frame, meaning it's going from a specific MAC address to another specific MAC address. This will get the ARP response back to router 3, and then router 3 will finally learn the ARP mapping it was trying to learn. And now, router 3 has everything it needs to put together the appropriate layer 2 header, which will take this packet across its final hop to host C. Router 3 will put that onto the wire, where it'll arrive on host C. Host C will strip the layer 2 header. Host C will strip the layer 3 header, and host C will finally process the data. And as with most internet communication, when you send something, you generally expect a response, so host C is now going to send that response back to host A. Host C will throw a layer 3 header onto that packet. That layer 3 header is going to have a source IP address of host C and a destination IP address of host A. Host C knows it's trying to speak to something on a forward network, so host C knows that this must be sent to the default gateway, in this case router 3. And host C happens to already have the ARP mapping for the default gateway, so it has all the information it needs to put together this layer 2 header, which includes the destination MAC address of router 3. Host C will put that onto the wire, where it'll arrive on router 3. Router 3 will strip the layer 2 header, and then router 3 will take a look at its routing table to determine where to send this packet. The destination IP address of this packet matches the default route, so router 3 will send that packet out towards the internet, where it'll finally arrive on router 1. Router 1 will take a look at its routing table and compare the destination IP address to see which route matches. In this case, this destination IP address matches our directly connected route, which means router 1 knows that this packet will be delivered to its final hop. And router 1 happens to already know the ARP mapping for this particular destination IP address. So router 1 has all the necessary information to put together a layer 2 header with a source MAC address of router 1 and a destination MAC address of host A. That will get sent onto the wire, where it'll arrive on the switch. And again, the switch has nothing new to learn, so it'll simply refresh that entry in its MAC address table. Then the switch will look at the destination MAC address to determine that this frame should be sent out port 4. The switch will put that onto the wire, where it'll arrive on host A. Host A will then strip the layer 2 header. Host A will then strip the layer 3 header. And finally, host A will process the response from host C. And that, my friends, is every single step that is necessary to get a packet from host A to host B and back, and host A to host C and back. And that is how these 3 tables were used to facilitate that entire process. The last idea I want to leave you with has to do with a very common interview questions for networking engineering type roles. That interview question looks something like this. Tell me everything that happens when you type www.google.com into a web browser. This question is trying to see if you can apply what we learned in this video to the simple act of visiting a website. Browsing to a website essentially involves 2 phases. First, using DNS to resolve a domain name into an IP address. And second, sending an HTTP request to that IP address. Well, in our illustration, the first thing we did was send a packet from host A to host B. But what if this packet was actually a DNS request? And what if host B was actually a DNS server? The response from the DNS server would have given us the IP address of the web server for the domain you're trying to visit. Well, what if that web server was actually host C? Then that packet that we sent from host A to host C would have actually been an HTTP request. So you see, everything we did in this video was in service of answering this very common interview question. And now you can confidently answer this question when you inevitably come across it. But it's more than just an interview question though. It's a fundamental part of understanding how internet connectivity works. Next time your friend or coworker or customer or parent asks you why they can't access their email or their favorite website, you'll know exactly what should have occurred if everything was working, and you'll be better equipped to troubleshoot and identify exactly where the failure might be. And with that said, we bring this lesson and this entire module to a close. If you followed each of the lessons in this module, then congratulations. You can now say you understand how data moves through the internet. If you're looking to become a network engineer, there is no better start to that journey than this video series. And if you're in any other IT or tech role, then now you have a better idea of what it is those networking folks do all day. And this type of cross-discipline training will pay off exponentially as you can now interact with your networking team much more efficiently. I truly hope you have gotten a lot out of this series. If you have, I'd love to hear about it. What was your favorite lesson? What topic did you enjoy learning the most? Tell me about it in the comments. Additionally, you can help me out by liking, subscribing, and sharing this video with a friend that could also benefit from understanding networking. That would really help me out, and I appreciate it greatly. Otherwise, thank you for watching, and I'll see you in the next one.